Here is the fourth type A meso-ionic molecule, and it is 1,3-oxathiolium 5-olate meso-ionic. And in this, I want to talk about the synthesis as well as the chemical reactions for this particular molecule. So starting with the nomenclature and the structure first of all. And as you people are already aware of the rules regarding the numbering, so we can say here that as this structure contains two heteroatoms, the first one is oxygen and the second one is sulfur. So the preference should be given to the oxygen heteroatom here, right? And the numbering should be done in such a way that the sulfur atom should get the lowest number, and it will be in this direction here. It will be in this direction here. And as you can see here that at position 1 we are having what? We are having oxa. On position 3 we are having the sulfur, means the thiolium. So it will be ended by the olate, which is actually present at position 5, which is very clear from this structure here, right? So the name will be 1,3-oxathiolium 5-olate, and this is the structure of this meso-ionic molecule. And regarding the synthesis, it can be synthesized from a similar type of cyclodehydration reaction using a reagent that is what? That is the trifluoroacetic anhydride, having a structure something like this here. Okay, so here is the reaction. You can have a look on this, starting from this type of reactant molecule and simply adding in that trifluoroacetic anhydride results in the formation of our desired meso-ionic product molecule, right? And the thing here is that why it is known as the cyclodehydration reaction. The reason is quite simple, that because with the aid of this trifluoroacetic anhydride, that is actually a sort of dehydrating agent, it results in the removal of a molecule of water, and that is why we are referring it as a dehydration type of method, in which finally what is going to happen is a bond formation will take place in between this oxygen and this carbon atom here, that will actually result in the formation of a 5-membered cyclic ring, which will be this here, right? So as it is leading to the formation of a cyclic structure, so it is better known as the cyclo type of dehydration reaction. Okay, and we have seen that this is actually a common method, and it has been employed for the synthesis of other meso-ionic molecules as well, which we have discussed in our previous video lectures, right? So a similar type of mechanism will be there, but this time I will be talking about the mechanism in a little detail here, right? So let us have a look on the mechanism. So here you can see this is the reactant molecule. This is the starting reactant molecule here. And now in this we can show the lone pairs which are present here on the sulfur atom. They are shifting like this, sending these pi electrons onto this oxygen atom in this way, right? So it will not be good to show such an arrow here because it is just a resonance. So better to show an arrow like this, which is double-headed, right? And moreover to put a square bracket here. So this is nothing. This is actually the second resonating structure for our reactant molecule, right? And now when we will be adding our reagent here in this, which is trifluoroacetic anhydride, what is going to happen is this negative charge will be going to attack as a nucleophile on this carbonyl carbon of this anhydride, sending these electrons onto the oxygen atom like this, right? So what is going to happen is this will now become a single bond carbon, single bond oxygen with a negative sign here, right? And on this side we are having this whole group here in the same way. It is present here, C double bond O and CF3 here, right? So now what is going to happen is this negative charge will further be present in resonance like this, sending these electrons onto this oxygen atom, such that now this will become a C double bond oxygen, right? A C double bond oxygen, which is also having one CF3 here like this. Okay, so this means it will simply result in the formation of a bond in between this oxygen here and this carbon atom of the trifluoroacetic anhydride, and this part of the molecule will be eliminated from the system in this form here. Okay, so this oxygen here will now be having a negative charge like this, and because of the bond formation in between this oxygen and this carbonyl, now we will be having an intermediate something like this. Being an active type of anion, what it can do is it can abstract a proton, something acidic in nature, resulting in the formation of one OH here. Okay, and we do have one such OH, or let us say a carboxylic acid in this intermediate which is having acidic protons. So what is going to happen next is that it will be releasing one H positive ion, resulting in the formation of an intermediate like this here. And moreover, what is going to happen to this, it will now result in the formation of one OH here, and the rest of the molecule will remain as it is. I mean, the trifluoroacetic acid will be the byproduct here, right? So because it is giving its H positive ion and that is going to this O negative, it will result in the generation of this thing, and this will result in the formation of this type of intermediate, right? And now after that, what is going to happen is, because this carbonyl here is having a partial positive charge, and we do have an internal type of nucleophile, or let us say within the molecule one nucleophile is also present. So this is going to attack here on this carbonyl carbon, being electrophilic, sending these electrons onto the oxygen atom. It will now become a negative charge and a single bond here, and after that once again the shifting of the electrons will take place, and these electrons will once again come here and resulting in the cleavage of this bond, sending these electrons onto this oxygen atom, which you can see here, right? So what I mean to say is that this fragment here will now be cleaved from this intermediate, giving a negative charge to this oxygen atom like this. Okay, and moreover, this whole fragment here will be shifted to this oxygen atom because it was acting as a nucleophile in this step, resulting in the formation of a bond between this oxygen atom and this carbonyl carbon of this CF3 fragment, right? Which you can see here, the bond formation has been taken place in between this oxygen and this C double bond O and CF3, right? So in short, we can say here that whatever fragment is present here, which I have encircled in this red color, that will be shifted from here to here, giving a negative charge on this oxygen atom because of the cleavage of this bond from here, and both the electrons are going to this oxygen atom, giving this type of intermediate, right? And finally, what is going to happen is that this negative charge will now act as our nucleophile. It will now act as a nucleophile, and now it will look for some electrophilic sites so that it can attack on that, right? And in this case here, we do have two electrophilic sites. The first one is this here, and here is the second one, and both the carbon atoms are having the partial positive charges, right? So now we have a little problem here, that out of this electrophilic carbon and this electrophilic carbon, on which side this O negative will be acting as a nucleophile, and it will be attacking on either this one here or this one here, right? So here we can say that if it will be attacking on this carbonyl carbon, resulting in the formation of a bond in between this oxygen and this carbon, and if we start counting the number of atoms in this cyclic structure which will be obtained thereon, it contains 1, 2, 3, 4, 5, 6 and 7, right? So this means if this oxygen negative is attacking on this carbon here, it will result in the formation of a ring structure that will be 7-membered actually, right? And now let us also consider the other case in which it is attacking on this carbonyl carbon here. So in that case, we will be having some cyclic structure, which will only be having 1, 2, 3, 4, and 5 membered ring structure, right? And we all know that the 5-membered rings are more stable as compared to that of the 7-membered ring structure. So definitely, without any doubt, we can say here that this oxygen negative will be going to attack on this carbonyl carbon, sending these electrons onto the oxygen atom, and this will become now a single bond oxygen negative here. And then reshifting of these electrons will take place like this, sending these electrons onto this oxygen atom, cleaving this part of the fragment from the rest of the molecule, right? So here you can see that attack of this oxygen negative on this carbonyl carbon is actually resulting in the formation of a bond like this, right? And when the negative charge will again come back on this carbon and oxygen bond, it will result in the formation of a double bond oxygen, and the rest of the molecule, you can see here it is present like this in the form of an anion, right? And after that, this anion, what it can do is it can abstract one acidic proton, and yes, that is present in this intermediate molecule here, and it won't be difficult for you people to recognize that acidic proton, it is actually this one here, okay? The reason being, this position here is alpha to the carbonyl group, and the alpha positions to the carbonyl group, they are highly acidic in nature, right? So what it will do is this O negative will be going to, it will be going to abstract a proton from here, I mean here, resulting in the formation of OH here, and the rest of the molecule will remain as it is. And what will happen here is, after that abstraction, a negative charge will now appear on this carbon atom, which you can see here it is present like this, right? And finally, this negative charge can be shown to be present in resonance in this way here. And once again, better to put here a double-headed arrow like this, because this structure here and this structure here, they are actually the resonating structures of each other, right? So what will now happen is a double bond will now appear in between this carbon and this carbon atom. So it will finally result in the formation of this molecule here, and we can always draw an equivalent structure, and that will be like what? That will be R1 single bond, this 5-membered ring structure containing 2 heteroatoms. The first one is oxygen, the second one is sulfur, and here is the second substituent, and this is O negative and a positive charge delocalized over this 5-membered ring structure like this, okay? And this is what, this is my 1,3-oxythiolium 5-olate meso-ionic molecule, for which we are trying to carry out this reaction starting from this type of reactant and using trifluoroacetic anhydride as our reagent, which is actually a sort of dehydrating agent. And this whole reaction, we can give a name to this. And what is that? It is a cyclodehydration reaction. And now let's talk about the chemical reactions for this meso-ionic molecule. It actually shows a similar type of reaction. I mean 1,3-dipolarcycloaddition with a variety of dipolerophiles, right? And here in this picture, you can see that this is our meso-ionic molecule, and it can behave as a 1,3 type of dipole, and the reaction with some symmetrical type of alkyne, which will actually be acting as the dipolerophile in this reaction, will result in the formation of a cyclic type of adduct as the intermediate, right? And finally, it will be undergoing an elimination of a molecule of CO2 like this here, resulting in the formation of a substituted type of thiophene derivative as the final product, okay? And moreover, I have mentioned here that the reaction is, of course, the 1,3-dipolar cycloaddition with a concerted type of mechanism here, okay? And now it's time to go into the details of this mechanism. So here you can see that we can always show an equivalent structure for our meso-ionic molecule. Let me write here, this is our starting meso-ionic molecule, and an equivalent type of structure will be like this, in which If we draw an axis of symmetry passing through this oxygen atom, we just have to do what? We just have to put two double bonds, the first one like this and the second one like this, okay? And of course, a positive charge will appear on this sulfur atom, such that now for this equivalent structure, I can always draw a resonating structure, and that will be like this here, giving a negative charge on this carbon atom, and this will now become a double bond oxygen, right? So once again, I can show this thing in the form of square brackets, because this is nothing, this is simply a resonance here, right? And after that, as you can see here, the interaction of our dipolarophile, I mean this symmetrical alkyne, will be like this here, right? So because it is a symmetrical type of dipolarophile, so there are no issues regarding the regioselectivity. The negative end of our 1,3 dipole, I mean this one here, it can interact with any of the carbon atoms, resulting in the formation of a transition state, something like this, right? So here you can see that the mechanism is actually a concerted mechanism. As soon as a new bond in between this negative end of the dipole and this carbon of the symmetrical alkyne will begin to form here, this pi bond out of this triple bond will be going to break, and simultaneously this new bond will also begin to form, finally resulting in the breaking of this bond in between carbon and sulfur, right? And the important thing here is that everything here in this transition state, I mean the bond making and breaking, it is all occurring simultaneously at the same time, right? And this will result in the formation of a cyclic adduct, something like this, okay? So we have encountered such kind of reactions and mechanisms in our previous lectures also, okay? And the only thing here to understand is that how to decide whether the reaction will stop here at this cyclic adduct stage, or whether it will be going further, removing some simpler molecules like CO2, giving some other type of product here, right? So you can see here I have written that this reaction won't be stopping here at this stage. Whatever cyclic adduct we will get here from this type of mechanism, it will be undergoing further type of reaction, eliminating of course a molecule of CO2 and giving some more type of stable product, right? And now it is time to understand that why the reaction won't stop here at the cyclic adduct stage, and what is special in this intermediate here after the removal of a molecule of CO2, that it is going in this direction, right? What I mean to say is that why the reaction is not stopping here, and it is giving a molecule of CO2, thus generating some intermediate which is having a positive charge here on this carbon atom. So this obviously means that whatever structure we have got here, I mean this intermediate, it is actually stable here, right? The positive charge is actually stabilized by something, by some effects here, and this is the reason why this reaction is going towards a more stable type of structures, right? So let us see here that why this positive charge is stabilized. There are basically two reasons for this. The first one is because of the presence of an allylic system here, right? So here you can see actually the presence of an allylic type of system. It consists of 3 carbon atoms with 1 double bond and a positive charge on the terminal carbon atom, right? So actually this can show resonance in this way here, giving a double bond, and the positive charge will shift here on this carbon atom like this, okay? Now the physical meaning of this resonance here is what? That the positive charge which was initially present on this carbon atom, it is not localized here, okay? The resonance here is proving that this positive charge is being delocalized over the 3 carbon atoms. Thus the dispersal of the charge will take place, that will lead to stability in this carbon atom having this positive charge, okay? So because of an allylic type of stabilization, resonance stabilization, I mean this positive charge here is quite a stable type of species, right? And there is also present a second reason that why this positive charge is stable here. If you go back to the this reaction, you will see that the R1 group here is mentioned to be what? It is mentioned to be a C6H5, means the phenyl group, right? And which is something like this. And we can also show that this carbon atom having this positive charge, I mean this one here, it is further present in resonance even with this phenyl ring in this way, right? So you can see here, this is the first structure, this is the second resonating structure, followed by a third, and this is the fourth one here, right? So this means that the positive charge is not only present on this particular carbon atom, it is actually moving from this carbon atom to this carbon atom up to here in this molecule, as well as it is also delocalized starting from here and covering the whole of the benzene ring like this, and then it is coming back to this carbon atom, right? So this means the positive charge is not concentrated here only on one carbon atom. It is actually present in the dispersed form covering this whole ring system here as well as this allylic system here, right? So dispersal of charge always means stability. So this is the reason why the reaction is not stopping at this stage, and it will be releasing a molecule of CO2 giving this type of intermediate here, right? Which you can see I have drawn here once again on my next slide. This is that intermediate having positive and this negative charge, and it is quite stable here, right? And now by drawing an equivalent type of structure for this structure, it will be like this here, right? And finally what is going to happen is this negative charge will shift here, sending these electrons onto this side. And why it is happening? Because although this positive charge here is stable, but at last in chemistry, charges always means instability, right? So this intermediate here will be doing something so as to disperse all these charges, so that to neutralize all the charges here. And one more question which may arise into your mind is that why it is not forming a bond like this, okay? Means on one side we are having a positive charge and on the other side we are having a negative charge. So why they are not forming a bond like this? The reason is quite simple here, because that will result in the formation of a three-membered ring here that will be unstable, right? So this will shift here, sending these pi electrons onto this carbon and carbon bond, finally giving one double bond like this and the second double bond like this, which is actually a type of a substituted thiophene molecule, right? So this is all about the 1,3-oxathiolium 5-olate meso-ionic molecule. And it is the fourth meso-ionic molecule which we have just discussed, and we have seen what type of synthesis or synthetic preparation is there. It is quite similar to other meso-ionic preparations which we have discussed in our previous videos, and moreover we have also seen what type of chemical properties it can show. It can undergo 1,3-dipolar cycloaddition reaction with dipolarophiles, resulting in the formation of a cyclic adduct, which finally gives a molecule of CO2 depending upon the conditions, right? If R1 is some other group, let us say this R1 here is some electron withdrawing group here, in that case, of course, this will be destabilizing this positive charge here, because it will be intensifying this charge because of its electron withdrawing capabilities, right? So in that case, it may be possible that the cyclic adduct formed here, it won't be going in this direction releasing CO2, because this thing is unstable in that case, right? So it all depends upon the conditions. So if it is a phenyl ring, it is stabilizing this charge, moreover this allylic system, it will definitely be going in this direction, releasing a molecule of CO2 to give this, and finally some reorganization is taking place, giving this type of thiophene molecule. But if the conditions are not allowing this thing, the reaction will stop here at the adduct stage, because that will in turn be more stable as compared to this type of intermediate, and it will not going in this direction. It will simply stop here at the stable adduct stage, right? So this is all about this lecture. Thank you so much.